Hey everyone. Do we need to wait 1 or 2 minutes, or do you know people that should come, or should I start? If no one disagrees, then I think I'll start. Okay, let's go then. C'est bon pour toi? Okay. So hi everyone. I'm very happy to be here to be talking about our research at MetaMask. I'm Vincent Eli. I've been involved in the Ethereum space since 2016, and I've joined MetaMask in last November. And thank you for being here. I know there is a lot of competition now with almost 5 or 6 stages. When I first talked in Paris at the Ethereum Conference 2 years ago, as a comparison, there was only 1 stage. So it's growing very, very quickly. The subject of today's talk is going to be about what we call, mysteriously, MetaMask. In a few words, it's the will to allow MetaMask to go beyond its current state, which is a layer 1 transacting wallet and layer 1 application wallet. And it's the will to go beyond that, and namely allowing for layer 2 solutions. And today, I'll be presenting the first step of this research effort. And the first step is what we call application keys, and we've made an Ethereum improvement proposal for that. Okay, so this research originates from the will to allow MetaMask to go layer 2. That was my objective when I joined MetaMask in November. And the first things we tried was to include or integrate a given layer 2 solution. But there are many. So we tried to play around, for instance, integrating Plasma. But when you look at Plasma, you have plenty flavors of Plasma. So should we integrate Plasma Cash, Plasma Debit, Plasma Monoplasma? That's a question we didn't decide to solve. Or we could also choose to integrate payment channel networks, state channel network. So the first approach could have been to pick one or a few given solutions and integrate them. Instead of that, we decided to focus on taking a more global and agnostic approach, which is to evolve MetaMask in a way that allows to create a framework such that MetaMask can better integrate with any layer 2 solution, and not only layer 2 solution, any crypto permission and sophisticated crypto permissioned application. So it can be layer 2, but not only privacy solution or even other stuff. I'll explain later. And to do that, to extend MetaMask beyond transacting layer 1 wallet, we have roughly identified 2 steps, and I'll be talking about the first step today, which is application keys. How do I? Okay, here. Application keys. And the next step, which probably will be the topic of a future talk or a future EP, is going to be about extensibility, how we can use those application keys to extend MetaMask beyond what it is today. So application keys. So the topic of today is roughly mimicking what has been written in this EP that we proposed 1 or 2 weeks ago, actually like 10 days ago. It's EP 1775. And it's a draft, and we labeled it as a ERC, Ethereum Request for Comment, because the aim is to develop a standard. And to develop a good standard, we need inputs from all points of view. So we have a discussion for that, which has been quite active on Ethereum Magician, but you don't need to write up this link. All you need to remember is 1775, because there you get the links to the discussion and you can see the EP file. And the idea is to develop a standard for new type of accounts, which I'll explain in a few minutes. But we really like to encourage wallet developers and application developers to look at this standard and tell us if they like it, if it lacks some stuff, if we should take another alternative approach, and so on and so forth. So the simple summary of this talk, if you need to focus for one slide, just one slide, you can focus now. The idea is that sophisticated crypto applications, they require many more than we have today in current wallets. They require a significant amount of crypto actions. So an action in a sophisticated crypto application, such as a layer 2 solution, may require you to do several signing in one step. Sign a transaction, sign a message, sign a second message, and then maybe countersign something that your counterpart is sending. So with current wallets, it will require like 4 or 5 clicks, one for each signature. And also sophisticated crypto applications require you potentially to delegate signing. If you are going to use a state channel, and the design of this state channel would be that every time your counterpart sends a message, you need to countersign it. It means you need to be ready. If you're using current MetaMask, you need to be ready, waiting for the pop-up to appear and sign it. So you need to be waiting in front of your browser for that. You cannot automate it. You cannot automate this process in any way. So current wallets have a bad UX for sophisticated crypto application. And this leads to security and privacy issues because basically you are using your main accounts, the one that holds your funds, to interact with applications. So you'll be signing message for different applications from the same account, and also you'll be potentially signing message from an account that holds a lot of funds. So if someone tricks you into signing the wrong message, it may have bad consequences, and also privacy issue because someone can link all your blockchain activity to a few accounts. That's why we introduce a new type of accounts. So these are not going to replace your main accounts, the one you currently have in your wallet. These are accounts that should be used alongside your main accounts. Those accounts, the will is to derive them in a way that is specific to your application. So they will be isolated for each application. And this can allow wallets to implement a more permissive and flexible behavior and security standards for those accounts. So basically the idea is that you would use your main accounts for transacting, the one that are currently standardized in wallet for now, and you would use app keys to interact with application, maybe initially funding them from your main accounts. Abstracts. So application keys, account isolation across applications, accounts that are specifically managed and derived for your application. So it gives more power to the app developers. And it allows also app developers to request some signing delegation. So they could use these accounts to sign stuff without prompting the user. I'm going to give now the specification. And basically what we need to determine for the specification to be complete are a few things. We need to determine how to identify applications. So what's a unique identifier we can use for each application. We need a way to properly authenticate each application. When an application is claiming to be some domain, how do we know it's the right one and it's not trying to steal keys from another account, from another domain? And how to derive those accounts using HD, hierarchical deterministic derivation. And what's the API to use those accounts? So that's what I'm going to present now. Motivation, I already said a bit about this, but in more technical terms, Ethereum wallets currently use a few standards. Those come, initially they come from Bitcoin. So we have BIP32. BIP32 is the specification of those derivation paths using indexes and the ability to harden these addresses. I'll talk a bit more about hardening later, but basically it allows you to isolate your account such that one cannot guess the public key of your child account from your parents' accounts. So is anyone here not familiar at all with hierarchical deterministic derivation? or can I assume some basic knowledge and move pretty quickly? Okay, so I hope that's fine then. So BIP43 is the next step that Ethereum accounts are using in their standard, is this idea to have this purpose field. And they all use, Ethereum accounts, they all use BIP44. BIP44 is, so you use the purpose field 44, and then you have the coin type. And BIP44 is this specification, all those fields. And what BIP44 says is that you can look at this list, SLIP44, which tells you that Ethereum is coin type 60. And basically all Ethereum wallets, they use this derivation path, where n is your account index. So first account in MetaMask would be this using n equals 0, second one n equals 1, and so on and so forth. And this is basically the standard for account derivation, and then we have API for Web3, RPC, and we have IP 1102 for privacy. But there are several things that you cannot do today in classical wallets. You cannot easily and in an easy, manageable way use different accounts for each application, or you will have to remember which accounts you are using for which application. You cannot use throwable keys, or you need a way to remember that you created this account for one time, but it's going to persist in your MetaMask list of accounts, and it's not going to be manageable. You cannot have signing without prompting. You cannot sign from your account without broadcasting the transaction. So, and we get some requests for that. Some say, we like to be able to sign transactions from MetaMask, but not broadcast them right away. Maybe we wait for 1 hour, or we wait for some condition to realize before we broadcast the transaction. This is not possible with the current way it works. Because for main accounts, you don't want this behavior. For main accounts, you want to broadcast transaction right away. And this is why we think we need, and all this, sorry, last thing, all this while using accounts that should be only restorable from your mnemonic. We don't want you to have to back up additional data. Only your 12 or 24 word seed or your hardware wallet, and then you get access to a standard that allows you to do all those things that are not possible today. So this is the motivation. And the specification. So application I already explained. I'm going to have to skip a little bit because I want to get to the end of this talk. So this is the standard we propose. So to interact with applications, which can be Ethereum application or other type of applications, we are proposing to derive accounts using this path. So it's going to use BIP32. BIP32 is the hierarchical deterministic derivation path that specify indexes and the fact that you can harden indexes. And we are going to use BIP43. So BIP43 is just this purpose field, the second one after the mnemonic. And this field, we are not going to use 44, like in the BIP44 standard. We are going to derive from that because here we are going to use a different structure. So it's different than what we're using for now for main wallets. It's different than BIP44. So that's why we're going to use a different purpose field. And then we propose to use 3 parts in the path that is used to derive accounts specific for each application. We use a persona path. This path allows the user to potentially use different identities with the same application, with the same mnemonic, and the application will not be aware that it's the same user. So maybe you use that from your mnemonic to create a work and a personal account, or you use that in any way you like. Second part is going to be an application uniquely assigned path. This part will be determined in a unique and deterministic way using the application domain. I'll explain how. This part is known by the application and it's deterministic. And the last part is what we call the application custom path. And this path will be under the application control. So the application may use this part to include, for instance, a version field, to create several accounts, and they can do what they like. Personas. So the first part of the path is the persona path. So this one is easy, it's just the IP number that we use as a purpose field. This one, persona path. This one is under control of the wallet and the user. Maybe the user wants to manage personas for the wallet wants to manage personas for the user in some way. Maybe it just uses incremental indexes, persona 0, persona 1, persona 2, or maybe it's something more sophisticated. This is going to isolate the HD tree. For each persona, we'll get a different tree. And the next part is going to be the application part of the tree. This part of the derivation, of the hierarchical derivation, is going to be using the application name, and we are going to use the domain. So we use either an ENS domain, or we can use a DNS domain, a classical URL domain. And we use, basically from ENS, we use the hashing scheme, which is that we hash the domain name, we split it first. So foo.bar.if is going to be split in foo.bar.if, and you hash it recursively, starting from the end. So you hash if, then you hash the result of that, and you hash bar, and then in a similar way with foo and the result of the previous operation. And you use Keccak 256 for that. This gives a unique application identifier. So any name, so we can use foobar.com as well. This will come to a unique 256 bits identifier. Then we split this identifier in a way that is compatible with the BIP32 standard. BIP32 standards require the indexes in the path to be 31 bits. So we need to split in 266 bits, or 32 bytes, is going to be divided in 60 times 16 bits, or 60 times 2 bytes. And it's going to be a path like that. We can use alternative maybe to split it in some other way, but the gist of the idea is to split in a way that is compatible with BIP32. So an example would be foobar.if. So we already seen how we derive this unique identifier. Then we split it in 16 equal homogeneous parts. Then we propose here to harden the indexes to be sure that the app are fully isolated. So if you leak in some way your public keys from one app, you won't be able to derive the public keys for another app. So this is in X, and then we translate it to unsigned integers. So this was the application derivation path. We had the persona path before. And the last part is the application custom path. This path can be managed by the application itself. We don't impose any constraint on it, except that it should be BIP32 compatible. So let me give you an example of the whole path. So let's assume, so the heap is pull request 1775. So let's assume this is the final heap number. So the first purpose field of BIP43 standard is going to be 1775, and we harden that. Then we use a persona path. So let's assume in this dummy data that the persona path that the user wants to use is 0 harden, 712 harden. So this is his persona path, and if he uses a different than that, for the same application, he's going to derive different accounts. And the application won't know it's the same person. Then we have the foobar.if UID path, which is there until here. And then here, the app custom path is going to be used by an application in the following way. They decide to include an index for their version, which is here 0, and they harden it, and then they use a set of accounts index and account index. So they use that way. But you could think of an application that wants to use this custom path in a very simplistic way. They would just they would remove those two fields, and they would just use 0, 1, 2, and so on here. now that we specified how we derive those accounts, we need to explain how our application can use them. So application will still be able, of course, to use main accounts in the same way as currently. They use the provider, or they use the Web3 API. Now we'd like to introduce new RPC methods or a new Web3 API or an app key API. And this app key API should allow the user to use those methods. So the first one will be enable. You request from the user to get access to this set of accounts. The user accepts, and potentially we can include there a challenge that the user automatically signs when he accepts to use those app keys. And we can do it in a way such that it's a one-time request, and then the next time the user can right away log in into those websites, and the app keys will be automatically activated. Then we use Ethereum signing methods. So here it's just you have a method to get the public key for your account, to get the address. You can derive public keys from parents' keys, and so on and so forth. Then we have signing methods. So here it's Ethereum signing methods, but we could use different kind of signing methods. We could introduce here Bitcoin signing methods, or even non-cryptocurrency signing methods. All those from the same derivation path specific for your application. So let me skip a bit this, and I'll finish by giving an example, because I think my time is almost over. So what you can do with that is that you can use app keys to create a website, for instance, that will allow you to have accounts for which the user can sign transactions, and you don't broadcast them right away, and you broadcast them later, maybe using a script in the web page or using a server or something. That's one thing you can do. You can use token or application-specific accounts. You can use that to have non-wallet or non-cryptocurrency accounts. Those accounts, for instance, if you want to do, I don't know, a password manager, you want to do privacy zero-knowledge proofs, maybe we can include those type of methods using these app keys, which will not be Ethereum methods, so we need new accounts for that. And you can think about integrating state channel, because there you will be able to do more complex actions without prompting the user at every step. And finally, you can think of cross-cryptocurrency exchange, where it would create, you log in, you get accounts for all your cryptos, and you can do swaps, transferring your accounts transferring your funds to your own account for each crypto. And that's it for now. So basically, I really want to, if you need to remember something of this talk, is please go to this HIP. If you are a wallet or an application developer, please go to this HIP. Please review it. Please make sure that this standard is compatible with what you would like to develop. Think if there is some benefit from us, and if you need other stuff, please contribute and let us know that we should change this standard in some way, or we should include this method, and so on and so forth. So here are my contacts, and last thing, I'd like to thank you all. And sorry for being a bit long.